Okay, so we'll get started. The coming weeks, next Tuesday, homework A will be due, and then a week. Um, so it looks like March 30th should be a Tuesday as well. Okay, so that should be Tuesday for the number 9 to be due, and then the Wednesday when you guys return from Easter break, we'll have our exam 3. Okay. All right. And then for in seat, today I asked Alyssa and Taryn for the surface disinfection. Okay. All right. So let's get started on the lecture part. Last time we talked about electric generators. So basically, for an electric generator, you convert mechanical energy into electricity. So and then for the mechanical energy needed, you can take various forms, maybe chemical energy, maybe from gravitational potential energy or wind energy, etc. Okay, but the final step is always for mechanical energy to be converted into electric energy for electric generator. Okay, so the way we do this is to maybe go back to the previous figure here, that the mechanical energy will drive the turbine or the coil there, that is to be moving in the presence of magnetic field. So then the angle the magnetic field makes with the normal direction of the coil changes. Okay, so you can see if you have a constant changing angular speed here for the coil, then your electricity will be a sine function. Okay, now in some cases you may see a cosine function, so that doesn't matter because sine and cosine, they are exactly the same with a phase shift. Okay, so it would be just depends on the author's preference. Okay, so you might be occasionally see that's a cosine function. Okay, all right. So the electric potential generated by a generator is equal to the number of coils you have times the B field times the area of the coil, and then times the angular frequency sine times sine of omega t. Okay, angular frequency is 2 pi times f. So in that case, you can see there's a maximum potential generated, which is related to m times b times a times the omega. So the parameters before the sine function, that should be the maximum. So, and then when you have appliance, its specification. So usually those numbers are given as the root mean square quantities. Okay, so 120 volts of voltage we use here refers to the root mean square of it, not the maximum value. Okay, so the maximum value could be higher. It's around 100, I think 180 or so. Okay, for the maximum. The other way around, you will have electric motor, so which basically convert the electricity, electric energy into mechanical energy. Okay, so that's motors, how motors work. So basically, you can give it an electrical input, and then it will have an output of mechanical rotational or rotational motion typically. Okay, that's because when you send in the current into the coil, then there's a magnetic force that makes the coil rotating. Okay. And when you have an electric motor, then you will actually generate a backward potential opposed to the source, the electrical input source. Okay, so that's called back EMF. So pretty much for electric motor. So at the same time, it's generating mechanical energy. You can think about it's also a electric generator that generate the back EMF. Okay. All right. And we also took a look on transformers, which change the voltages. Okay. So you could have step-up transformer. That means you bring the voltage up. You could have also step-down transformer, which brings the voltage down from higher voltage. Okay, and for transformer equation, so basically the electrical power should be the same from the primary circuit of the primary coil of the transformer to the secondary coil. Okay, so in that sense, IPVP will be equal to ISVS. Okay, the current in the primary coil times the voltage in the primary coil should be equal to the current in the secondary coil times the voltage in the secondary coil. So combine those, you can get the ratio of you get out from the two ends of the transformers, the primary end and the secondary. So voltage on the secondary divided by voltage on the primary should be equal to the number of coils you have on the secondary over number of coils you have on the primary coil. Okay, and for the currents, they are the other way around. So current in the secondary over current in the primary is equal to the number of coils in the primary divided by the number of coils in the secondary. Okay. And we also look at the electrical safety. One more measurement you can take is to ground the case of the appliance to so connect the case of the appliance to the ground. That's called grounding. Okay, so that's one more precaution you can take. In addition to electric fuse and electric breaker, okay, the circuit breaker. And we also took a look on the inductance. Basically, if you have a coil inside a circuit, then if this is powered by a battery, you can see as the current goes through this coil, there will be magnetic field generated in the coil over here. Now, you should keep in mind that there should be also magnetic field by these straight wires, but because they are just single straight wires, so the magnetic field produced by those are pretty small compared to if you have a lot of turns of coils here. Okay, so then the primary effect we'll be looking at is the magnetic field inside this coil. Okay, so you have magnetic field inside this coil, then as the current is changing, then there's changing in magnetic field and then the magnetic flux as well as the result. Okay, so once you have changed magnetic flux, then you'll have induced EMF. You can model it as a battery like this, which will be opposed to the source that caused the change. Okay, so that's also called induced EMF or back EMF. Okay. The reaction of the coil to the signal, we call it inductance. Okay, so it's defined as so calculating from the voltage induced equals to the number of coils you have and then times the change in flux divided by change in T. So this is again from Lenz's law, all right? But the flux changing is proportional to the current changing as the rate of current changing. So you can also relate it to delta I over delta T with the constant number L. So L and then is the inductance for the coils in the circuit. So from here, you can derive that L is equal to N delta phi over delta I. Okay, delta T will cancel out there. Inductance has a unit SI unit of Henry or H for the abbreviation. So if we take a close look at the inductance for a solenoid, for example, so then the B field causes by the current going through it is equal to this, which we talked about in the previous chapter. Small n is equal to the total number n, capital N, divided by the total length L. So then the flux, magnetic flux change, if we start from 0, will be equal to number of coils times B times A equal to this guy, okay? And then we derive that this will be the inductance for a solenoid, which is the density of turns of coil squared times the area times L, okay? And when you have a solenoid in a circuit, we call it as an inductor, okay? And we also took a look at the energy stored in a solenoid. In the solenoid, there's a magnetic field. So this is equivalent to the energy stored in the magnetic field. Okay. So we can do this conclusion that the energy stored is equal to B squared times A times L divided by 2 times mu naught. Okay. Which if we divide the energy by the volume of the solenoid, we get the energy density stored in the magnetic field. Okay, so then you can see it's magnetic field squared divided by 2 times mu naught, which is constant. And if we look back at section 19.7, we saw that electric energy stored in the electric field actually is also proportional to the field square. Okay, and then multiplied by a constant, which is epsilon naught divided by 2. So these two are similar to each other. Okay, so they are both energy densities in stored in a magnetic field or in an electric field. They're both proportional to the field strength squared. Okay, so magnetic field B squared and then electric field E squared. All right, and then we were about to take a look on this example here. So let's take a look on this one here. So this one says a solenoid 1.8 meters long and has 450 turns per meter. What's the cross-sectional area of this solenoid if it stores 0.39 joules of energy when it carries a current of 12 amps? All right, so we can start with list the knowns. We have L given. The length is given as 1.8 meters. It tells us 450 turns per meter. So that's actually the number of turns per length. So that's small n, okay? It's 450 turns. And it says the energy store, U sub m, magnetic energy, is 0.39 joules. It tells us the current is 12 amps and asks us to solve for cross-sectional area. So previously, we know that for energy stored in a solenoid or a magnetic field, that's equal to B squared times A times L divided by 2 mu naught. Okay. So we have the L. Now we have this guy. And you want to solve for A, so you need to figure out what's B. Okay, so the B field. So the B field inside the solenoid, that's also something we learned, but in the previous chapter, so it's mu naught times N times I. Okay. So you can actually look this one up in the previous chapter, but I think we had it in a couple of slides back. Just over here, okay, the magnetic field in the solenoid is mu naught N times I. All right. So basically you can calculate what's your B field. And then once you have your B field, so from here you can calculate what's your B field. And then once you have your B field, you can put it in here. Okay. And you can solve your A. But we can say A is equal to, from this equation, you can do 2 mu naught. So multiply both sides by 2 mu naught, okay, times capital U M divided by B squared times L, okay. And then for B squared, you can take that as substitution there, mu 0 and I, and square this, okay. So that means you square each of those three terms times L, okay. So this is B squared. And 2 mu 0 um, all right? And then you can cancel out 1 mu naught here with the square, all right? So you can put your numbers in. 2 times 0.39 joules divided by mu naught is the constant of 4 pi times 10 to the minus 7, okay? And it's 450 squared. I is 12 squared, and the L is 1.8 meters. This is amps. All right. After that, you can calculate for your area. So this is area, okay? So area then is equal to 1.18 times 10 to the minus 2 meters squared. All right. Questions you guys might have? Okay. So today we are going to check probably maybe a couple new sections here in this chapter. So the first one we'll be looking at is an RL circuit. Okay, so this could be an analog to an RC circuit that we checked earlier in electricity. So in this case, if you have an inductor, which is a solenoid or terms of coils here, being placed into a circuit. Okay, so the simplest one you could have is this one is in series with the resistor. Okay, and then the whole circuit is powered by a battery over here. All right. So as you close the switch, you'll see that because this guy actually has the, according to Lenz's law, you're opposed to the change. So once you close the switch, the current will start to flow through the circuit. So once you have current into the inductor, it will generate a magnetic field, which causes the magnetic flux change. Okay, so this will have a factor opposing that current being added to the current. So then there will be back EMF on this guy. Okay, so then the current will start to change. All right, but with opposing effect from this guy. Okay, and basically, this can be shown, unfortunately, only by using calculus knowledge. So if you have a inductor, so you see a sign like this and an L. If you have the switch, so flip to this guy, which means it's powered by the battery. Now you'll see the current will build up, but actually little bit kind of slow. Okay, so it's not like linear going up, but it will turn out to be exponentially increasing, but then it will saturate. Okay, so it's a minus exponentially increasing. Okay. So, and then as I mentioned, this actually can be shown with the knowledge of calculus. So I'm not going to show it here today because the nature of this class. Okay, but this is the result you get. Okay, you'll get the current equal to this guy. All right. Epsilon is the voltage by the battery, the EMF of the battery. R is this resistance, and then 1 minus exponential minus of t, that's the time constant, or the time variable, times R divided by L. Okay, so this has similar form of this guy. Okay, a constant number times 1 minus exponential of minus t over tau, where tau is L over R in this case. Okay, for the RC circuit, you have tau equals to R actually times C. Okay, in this case, it's L divided by R. All right, but similarly, you'll see current actually goes up. Okay, and then reaches to an equilibrium point. Actually, I think for the RC circuit, actually the current goes down. Okay, so in this case, your current actually goes up. So there's differences there. All right, let's take a look on the example here. It says, how much time does it take for the current in an RL circuit with R equal to 130 ohms and L equal to 68 millihenry to reach half its final value? Okay. So on this guy, you are given, this is the RL circuit. Okay, so it's an RL circuit. And the current of RL circuit, that's the equation, that's equal to epsilon over R, 1 minus exponential minus T times R divided by L. Okay, so that's the equation. You're looking for what's T if your I is equal to 1/2 of your I final. Okay, at that moment. It tells you only R equals to 130 ohms and L equals to 68 millihenry. So you can do a conversion there right away. 68 times 10 to the minus 3. Okay. I will have you guys give it a try, and then we can take a look at the solution together. Okay, in a couple of minutes. So I think they have responses in. Let's take a look on this one together. So for IO circuit, so we can actually go back one slide. Over here, we can see that your current increases and then flat out a certain time. So this is the final current, I0 as your final current, which if you take a look at this formula over here, you'll see that if your t is infinity to large, then your I will be equal to epsilon over R. Okay, so I naught should be equal to epsilon over R. If you take a look on the equation and the figure here, you can realize that. Okay, so basically that would be your final current I0. So now let's go back to the problem over here. Right, so you can see your I final will be equal to epsilon over R 1 minus e to the minus infinity, right? Times t times R over L. When t is very large, that means the final status. Okay, so that's something you might take a note that. So t equal to infinity is your final. So then e to the minus infinity, that would be 0. Okay, so your final is actually epsilon over R. All right. Now you're looking for when this I is equal to half of your final. So that means your I is equal to half of epsilon over R. Okay, so that's what you're looking for, the time at. And now you can take a look on this equation back here. So your I is 1/2 epsilon over R, which is equal to epsilon over R times 1 minus exponential minus T times R over L. Okay. So it turns out you do not have to know the epsilon because epsilon and epsilon will cancel out. Actually, both the epsilon over R will cancel out in this case. Okay. So then you'll have 1/2 equal to 1 minus of the exponential function here. That tells you the exponential function should be equal to 1/2, right? Because this is 1 minus that equal to 1/2. So then this is 1/2. Okay. So your exponential function is equal to 1/2. Then and you are now solving for the t given R and L. Okay, t is over there, so you do line function to the both side of equation to get rid of the exponential function on the left. Okay, so on the left, then you'll just have minus t times R over L equals to line function of 1/2. Okay. Then you can rearrange your terms over here to get t. T will be equal to then minus L over R line of 1/2. Okay. So basically isolate t, move this R over L to the other side of the equation becomes L over R. Okay. So then minus, you can put in your numbers now, 68 times 10 to the minus 3 in the unit of Henry H. R is 130 ohms and natural log of 1/2. So then it becomes t equals to 0.363 times 10 to the minus 3 seconds. Okay. Or you can say 0.363 of milliseconds. Okay. All right. Let me know if you have any questions on this. there's time constant here for RL circuit. Okay, so RL circuit, I didn't write it specifically throughout this problem, but that's equal to L over R, the inductance divided by the resistance. Now remember, for RC circuit, a resistor with a capacitor, that tau constant is equal to R times C. Okay, so either R times C or L over R, they are in the dimension of seconds. Okay, because that's time. Tau is the time constant. Okay. All right. Okay. Now, when you have the switch over here actually flip to on, then you kind of charge this inductor. Okay, so if this is a capacitor, I think it was easy to understand that you are charging your capacitor. So this is similar concept, but we don't call it charging. Okay, so we simply just say you turn on the switch, then there will be magnetic field build up inside the inductor. Okay, so then there's energy stored there in that case. After a while, so then there's a maximum current reached for the circuit, then you have maximum magnetic field here. Now you actually can, so because there's magnetic field there, you know that there's energy stored in this um, solenoid. Now you can actually take the energy out, okay, afterwards. So you can switch it to switch 2 here. That means the circuit is turned off. Okay, so put this into switch 2. Then you kind of taking energy out of this. Okay, so then now after that, then the current will be, because there's current over here. Now you turn off the switch. That means you cut off the power, but your inductor will react to that. So in the sense of opposed to that change. Okay, so you will not, the current will not die away, die out right away because of that inductor here. Actually, it will decrease slowly. Okay, as exponential function down. Actually, I think that that happens quite quickly. Okay, so maybe if you look at the actual time, maybe 1 second or so. But when we refer to the circuit over here, so we know that it's not immediately, right? So it takes a little bit while, a time to die out the current. So then that energy is consumed by this resistor after you put the switch to the position 2 over here. Okay, so then this resistor will take the energy out of it. If you indeed have a light bulb over here, you'll see that once you cut out the power, you don't see the light go out immediately, but it takes a couple of seconds, okay, for the light um, to die out. So the current here decreases as a exponential function minus t over tau. Again, I0 is the initial current, which is if it was fully let's say quote charged, okay, then it's equal to epsilon over r, okay, and then again tau is L over r. Okay, so that's the kind of referring to the cold discharging process for inductor. Okay, all right. In that sense, we can take a look on another example here. This one says, given the figure showing here for a circuit, so you have a switch over here. You have power supply, which is a battery, and then there's a 110 ohms resistor. Now, this guy, this resistor, and this one are parallel to each other in a sense. Okay, so if this is closed, if the switch is closed, okay, so then this one 100 ohm and the 2 Henry inductor, they are in parallel to each other. Okay, if the switch is open, then you can see then these two are actually, the inductor and the resistor actually are in series. Okay, they are connected one after another in that sense. Okay, So it depends on if the switch is open or closed. It says find the current in the battery. Okay, oh, I think I forgot this to mention this. So it says inductor has negligible internal resistance. Okay, so um, if so, this is the case if not specified. Okay, so we will take the inductor to have negligible resistance because they are made of conducting wires. Okay, so that's very small. Okay, all right. So it says find the current in the battery 100 ohm resistor and the inductor immediately after the switch is closed. Okay, so if the switch is closed, then we have the inductor and resistor in parallel to each other. Okay, because they are both powered by the battery. You guys can think how you can solve for this one. I'm going to draw the circuit on the paper here. Okay. All right. So in A, it says what's the current going through this guy, and this. Okay, so the resistor, the battery, and then the inductor. So we can see if you have the switch closed over here, then the current goes out from the battery. Okay, so current will go out from the battery. So this is the current from the battery, and then it will split into one current goes in this way. So that's the current on the inductor. So let me say this is current on the battery, I sub B, and then split into another one, the I on the resistor. Okay. All right. So basically, when you have switch closed, they are parallel to each other. This guy and this guy, they are parallel to each other, right? So you can calculate their current separately. Okay. So on the right hand side of the circuit, so then this is a RL circuit, right? You have a resistor, you have an inductor, and you have a battery. Okay. So that's the left hand side of the circuit. Now on the right hand side of the circuit, then you have basically a battery, two resistors, they are in series to each other. Okay, so you can split in the circuit into two parts. Okay, because the two parts are in parallel to each other. Okay, so you can calculate what's the IR here because they are in series. Okay, and then you can calculate what's the IL here, right? Because this guy will be independent of that guy. Then the total current going through the battery should be the two add up, right? Because it split into two. Okay, so we can do that on that way. Let's take a look on the current on the resistor. Just looking at the left hand side. Let's put it in that way. Okay, so I of R should be equal to, you have two resistors in series, so then will be just epsilon divided by the total resistance, so 10 plus 100 ohms. Okay, you have two they are this one and this one, they are in series with each other. So this will be epsilon is 10 volts divided by 10 plus 100 is 110 ohms. Okay, so that will give you 0.091 amps. This is the current on the 100 ohm resistor. Okay, then you look at just the left hand side of the circuit. So this is for the 100 ohm resistor. Okay, IL, I on the inductor. So this is an inductor. So then you will be using the equation of, for when the switch is closed for inductor, is epsilon over R, right? Times 1 minus e to the minus t times R divided by L. Okay. In this case, your L is the 2 Henry. Your R is the 10 ohms. Okay. So it's asking you right after, immediately after the switch is closed. So that means the t equal to 0 moment, right? Just right after that is closed, so t is equal to 0. If you have t equal to 0 here, right? So and no matter what's R, what's L, it's going to be 0 on the power here, right? So e to the minus 0 is 0, e to the 0. So then this whole thing will be 1, right? 1 minus 1 will be equal to 0, right? So you don't have to plug in numbers here for this, okay? So it's going to be 0 amps. This is for the inductor, the 2.00 inductor, okay? This is right after the switch is closed. So then you have the current in the right, or in the resistor, and then current in the inductor. So then the current in the battery should be equal to the summation of the two, right? So it will be still 0.091 amps plus 0. So that's still 0.091 amps. Okay, so this is the current through the battery. Okay. So in A, we have the current for the battery, for the resistor, and then the inductor immediately after it's closed. The switch is closed. Okay. Now in B, let's take a look on the equation. The question is asking you find the current in the, again, the three elements: the battery, the resistor, and the inductor a long time after the switch is closed. Okay. So when it refers to a long time after it's closed, then t will be equal to infinity, right? That's what long time means. Okay. So after long time, let's take a look on this guy again. I on the resistor, we still, so this is still closed, and this one and this one, they are parallel to each other again. So you're just focusing on the left hand side of the circuit. So this is the same as epsilon divided by the 10 plus the 100 ohms. Okay, so it'll be the same as the in part A. Okay, that's for the resistor, the 100 ohm resistor. Now for the current in the inductor, this time because T is a different T, so that will be changing. So I on the inductor will be epsilon over R, 1 minus e to the minus. So T equal to infinity, so minus infinity, okay, times R over L. That should be still giving you in minus infinity, okay. So exponential to the minus infinity, exponential to the minus infinity would be 1 over exponential to the infinity, right? So if you have e to the infinity, that's still infinity, that should give you 0, right? So e to the minus infinity will be 0. So then 1 minus 0 should be 1. So long time after your current in the inductor should be just epsilon over R because 1 minus 0. And again, R will be 10, so this will be 10 volts over 10.0 ohms. Okay, you are just looking at the left side of the circuit. That gives you 1 amps for the inductor, the 2.00 Henry inductor. Okay. Now, the current in the battery should be the addition of the two currents. So 0.091 amps plus 1. All right. So now I think we look at the two parts of the circuit. Now let's take a look on the whole picture here. Okay. So if we take a whole picture over here, long time afterward. So long time afterward, there actually indeed will be no changing in current on the inductor. Okay. So then the inductor, there's no current changing, it will not respond to this guy. Okay, so then now afterward, it's not going to have any response on that. So this will be, you can treat as a straight wire. Okay, so if that's the case, then let's take a look on here. So long after, this is what you'll be looking at. On this one, you still have the 100 ohms. This one is 10, but on this guy, you'll be just looking at a straight wire, right? So then if this is just a straight wire, because the inductor has no response now, okay, so it's a straight wire. So what actually is going to happen is the current goes out from the battery, right? So current goes out from the battery, and then it will only flow to this side of the circuit backward, because the current doesn't like resistor. So then the current will not actually go in through this part of it, okay? No current. It will prefer to go through a straight wire instead of encountering a resistor. Okay, so then that tells us actually looks like the thing will need to change a little bit here. So on this guy, okay, it's not going to be having a current over there. So the current over here, it's going to be 0. Okay, so I on the resistor is going to be 0 for the 100 ohms. Okay, therefore that's the correct answer for the resistor. Okay, and then for the total current, so this one still holds. Okay, so it's still 1 amps. Now on this guy, this will become 0. Okay, so then I on the battery should be just the 1 amps. Okay, this is for the battery. All right, does that make sense? All right, because now after there's no response from the inductor, so it's just a straight wire. Okay, so then the current will not go through that. Okay, so this is the case. So if you have a straight wire in parallel with an element, so that means we are just skipping the element. Okay. All right. All right, so next, if we move to part C here, now you have this open. Okay, so you kind of like discharging, but cold, discharging. Okay, so this is kind of say discharging process of this guy, the inductor. Now, once you have this open, then the supply of current to this guy will be cut off, right? Then the current in here will die out. So then there's a change in current. So there's change in current, then there will be response from the inductor. Okay, so the inductor will appear again, but you can see the current actually goes through this guy, right? Now, if this is cut off, then current will go through the, in this sense, okay, through this resistor, and then goes back in that way, in that loop. So the energy stored in here will be then consumed by this resistor. Okay, so energy will be taken out by the resistor. So this is just a RL circuit. Okay, now these two are in series with each other. So it shows clearly there will be no current going through the battery because battery is cut off from the circuit. Okay, but I on the resistor will be the same as the I on the inductor because they are in series now. Okay. And for the inductor, it's going to be, this is a discharging process. So it's going to be, for the discharging process is the I naught times exponential or minus T over tau, or T times L times R over L. Okay. So either way, this is epsilon over R, okay, which is the 1.0 times exponential minus T R over L. Now it's asking for immediately after the switch is open. So this time T is equal to 0. Okay, when you have T equal to 0 here, the exponential function will be equal to 1. Okay, so this is 1. So then this is the 1. The current in the resistor and the current in the inductor will be the same as 1 amps. Okay, and the battery is going to be 0. Right. And then for the last part, again, it's asking you to find the current in the battery because this is open. So the current in the battery is still 0. And then the two are in series with each other. So they should have the same current of 1.00 as the initial epsilon over R times exponential to the minus. This time long after, that means your T equal to infinity. Okay, so minus of infinity times R over L. Okay. Again, minus infinity times the number should be equal to minus infinity. So e to the minus infinity will be 0. Okay, according to that. So this will be equal to 0. 0 times 1 will be still 0. Okay, so long after the switch is opened, then you should have no current in the circuit because now all the energy is being consumed, okay, by the resistor. All right. Questions you guys might have? All right, so if not, then we'll stop here for today, okay?